Hi everyone, welcome back. So today in this video we are going to briefly discuss statistics, probability and return period. And you may ask why we are doing statistics and probability in hydrology. So until now what we have done is we have looked at hydrologic processes in a deterministic way. What that means is we start with rainfall and we know how much of that water, or at least we try to estimate how much of that water infiltrates into the ground, how much of that gets evaporated, how much of that becomes runoff, and then eventually we get the stream flow hydrograph. Even when we did HMS modeling in one of our labs, we compared our simulated hydrograph with observed hydrograph, and then when the two were not matching, we calibrated our model. And so the idea of that deterministic model is that if you have the same set of parameters and if you have the same input, the output is always the same because it is going through the same processes and using the same parameter values to convert your input into output. So statistical hydrology or stochastic hydrology involves randomness. So as we all know, all natural processes are random, including rainfall. And if we think about hydrologic design, we are trying to design a structure thinking about the maximum flow it can handle in next 10, 50, 100 years. So we don't know what is going to happen in terms of hydrology over those period of time. So we try to incorporate that natural randomness in our analysis, and that's where the statistics and probability come into picture. So that's why we do this. So I'm assuming that many of you have taken some sort of probability class or statistics, and you know something about how to calculate probability, what probability distributions are, and so on. So in this video and some other videos that I'm going to do related to statistics and hydrology, I will just relate the statistical part to how we are going to use in hydrology, and I'm not going to go into detailed statistics. So again, just to refresh you, what is statistics? So statistics is about making inferences about the population of a random variable from a sample of that random variable. So population, sample, inference, random variables. So you may have heard all of this before. So in this video, we'll just see how that is used in hydrology. So again, I said this earlier, so why we do probability and statistics in hydrology. So in this class, at least we are interested in frequency analysis. So what that means is we are interested in looking at, from the hydrologic design point of view, what is the maximum discharge a structure needs to handle. So what you see here is a bridge that has been overtopped. So obviously the bridge was not able to handle the flow, so maybe it was under designed. So we want to know what's the maximum flow a structure that we are designing can handle from the planning and management point of view. So what you see here is an image, and there is a river or stream going through this area, and we want to know how often a flow of certain magnitude will occur. So whenever there is a very high flow, it is going to inundate some of these areas. Then we want to know how often that inundation will occur. If it is too often, then we don't want to do any development. If it is less often, then you can delineate that floodplain, and people can buy flood insurance and so on. So both for hydrologic design and water resources planning and management, we have to do statistical analysis in hydrology. That's why we are doing this. So just to refresh your mind about population, sample, and event, so many of you who have taken a statistics or probability class, you may have learned probability and statistics using a deck of cards and flipping a coin and so on. So what I'm going to do in this slide is I will use the right half for your traditional deck of cards, and here in this case let's talk about stream flow. So this is the hydrology part. So what is population? So when we think of deck of cards, so population, the technical definition is all possible outcomes. So when you have a deck of cards, we have only 52 outcomes. Okay, or 52 results, or basically 52 cards. So you have a finite set of population, so that becomes the population for deck of cards. But for stream flow, if you think about it, we know that it is greater than 0, and there may be some upper bound which we don't know to that stream flow, some Q upper bound, and then anything in between this is possible, right? So you cannot say that my stream flow is going to be 1, 2, 3, 4 until let's say 1 million CFS. It could be 1.001, 3.5, 9.7, 25,200 CFS. So it can have large number of values. So that becomes, so any possible value stream flow can take, any value that stream flow can take becomes the population. So that's what population means when we talk about stream flow, any possible values that will flow through a stream. Sample. So in terms of deck of cards, so a sample could be, let's say you have a 4 of heart, a 5 of diamond, a 3 of heart again, and so on. So you can again have a subset of population will become your sample. In terms of stream flow, you can say stream flow measured from 2012 to 2015. So 3 years of data that you have is your sample. So many times if we have measurements at a river, so most of those measurements, they were not carried out ever since that river exists. So many times you will see a stream gauge installed maybe last year or 10 years ago or maybe 100 years ago, but what you have is that 100 years of data, which is a sample. So you are never going to get the population associated with stream flow, unlike what you get for the deck of cards. So most of the stream flow data or any hydrologic data we use is a sample of that population. Okay, and we don't have the population, so we have to make certain assumption, and we will talk more about that later. So this becomes our sample. Any measurements that you have for a hydrologic variable, that is basically a sample. It's not the population because it doesn't represent everything that happened at that river at every instant. So even if you have long period of data, 100 years of data, if your stream flow was measured daily, then you just have one value for that entire day. You did not capture all possible values or that were happening every second. Okay, so as I said, most of the times we deal with samples in hydrology, not with the population. And then finally, event. So with deck of cards, if you pick a let's say 7 of diamond, so you pick a 7 of diamond, that becomes your event. Okay, or you pick another card, that becomes an event. So in hydrology, we cannot say a cube of 2500. You will rarely get a flow that will exactly match this value. Okay, so in this case, an event could be Q greater than 2500 and maybe Q less than 2600. So you will get some value between these two, and that sort of becomes your random event. Okay, and we'll talk more about this in the next slide. So probability and cumulative probability. So some of you may have heard of cumulative probability and some of you may not have, but I'm sure all of you, or if you have taken a probability or statistics class, you have heard of probability. So we always use this X random variable. So in terms of deck of cards, you say probability that X is equal to 4 of diamond, then that is 1 over 52, right? So that's the probability that you will pick a card that will match this 4 of diamond or 4 of heart. Or if you say X, let's say 10 of diamond, or X just say 10 of any, then that will be 4 divided by 52. So it could be 10 of diamonds, spade, heart, and so on. So you have 4 cards that has a value of 10, so that becomes 1 over 13. So that's the probability. So you know the exact probability associated with these events when you do deal with simple event like this within a deck of card. But in hydrology, as I mentioned earlier, we are not dealing with exact values. So X in this case will be a stream flow happening greater than 2500. And if I say and X less than 2600. So what I'm looking at here is not an exact value. I'm looking at a range that this random variable X can take. And when you are dealing with these kind of ranges, the probability that you are calculating is not this probability, it's the cumulative probability. So cumulative probability is X random variable taking value within a range. And the most common probability that we are going to see and used in high flows and flood frequency analysis is X greater than certain value Q. Okay, and this probability that X or Q, any random variable equaling or exceeding a certain value, that's called exceedance probability. And that's what we will be calculating in all the probability and statistics that we are going to do here. So remember, exceedance probability is a random variable, in this case discharge, equaling or exceeding a certain value. So you do exceedance probability when you are doing flood frequency analysis. When you are doing it for low flow analysis, then you say x less than or equal to a certain value. So for stream flow and flood frequency analysis, at least in this class, we are going to be looking at exceedance probability. Now coming to the next term that is commonly used, or the most important term. So many of you may have heard this 500-year flood, 100-year flood, and many people think that, oh, 100-year flood means if that flood happens this year, it will not happen again in the next 100 years. And that is sort of incorrect if you look at this statement. So this, again, this is actual news. So this news article is saying that Houston is experiencing its third 500 flood in 3 years. So if we go with that statement that 100-year flood happens after every 100 year, then a 500-year event should happen after every 500 years, not 3 times in 3 years. Okay, so that's why we need to know what return period means. So what I'm showing you on this slide is a time scale. So I'll just divide this into 3 parts. So what you see here, on the blue line is just time. In each circle represents 100 years. So 0, 100, 200, then there is 500 in the middle, 1000 here. So and then you see a flood event. So if we go with that definition that 100-year flood happens after every 100 years, so this is what you can expect, and this is not a very realistic definition of that 100-year flood. Okay, so this is not what happens in nature. I'm showing on the second that what you see here is we still have the same number of events, but they are taking place in just the first half or in 500 years, and then there is nothing. So we still have same number of events over a period of 1000 years, but they are distributed only in the first half, and the second half there are no floods. So again, this could be possible, but again, this doesn't happen very often in nature. So most of the times what we see here is the third case. So we have 10 events that are evenly distributed over a period of 1000 years. So the technical definition of return period is that over a period of long time, depending on your return period, so over a period of hundreds or even thousands of years, a T-year return period flood will have an average recurrence interval of T years. Okay, so what that means is that if you have 1000 years of data, so on average, you should be able to see the 100-year flood happening with an average recurrence interval of 100 years. So in this case, you can see you had 3 events in 2 years, but then there is no event here in this 100 years. So if you take this, then you will see there is 1 occurrence every 100 years and so on. So as I said, over a long period of data, you will see the average recurrence interval. So return period and recurrence interval are used interchangeably. So in this class or many of my videos, I'm going to stick to using return period term. So if this is the case, then the question is, how is return period then related to probability and statistics? Okay. So usually return period is equal to 1 over the exceedance probability. So we just discussed what exceedance probability is. So exceedance probability is probability that Q, so I'm just going to use Q as my random variable for discharge, Q greater than and equal to some value. Okay, so that value can, let's say K. Okay, so if we know the exceedance probability for a certain Q threshold, then the return period will be 1 over that exceedance probability. Or if you know the return period associated with a certain flow, then the exceedance probability will be 1 over that return period. So in practice these days, many times instead of using the definition of recurrence interval for 100-year flood, we say that there is a 1% chance. So this 1% is 1 over the return period, which is 100. So there is 1% chance or probability that the 100-year flood will occur every year. So a 2-year flood, there is a 50% chance. So 50% is again 1 over T. T in this case is 2. So instead of saying a 2-year flood, we say a 50% chance probability that this flood will occur every year. So same with 100-year. Instead of saying a 100-year flood, a good way to say that is that there is 1% chance that this flood may occur every year. So that way it takes away this notion that, oh, if I get the 100-year flood now, I will not get this for another 100 years. So with this, I'm going to stop here in this video. In the next video, we'll focus more about on how to get this exceedance probability so we can calculate return period, and then how to do flood frequency analysis. So we will do that in the next video. So in this video, I hope you were able to understand the concept of population, sample size, and event in the context of stream flow or flood frequency analysis, what exceedance probability is, how it is different than the regular probability, and how the return period and exceedance probability are related. So with that, I'll stop here and I will see you soon in my next video. Thank you and bye.